So today we'll study about how a circular current loop behaves as a magnetic dipole. Before we proceed there, let's recall for a moment the expression we derived for a magnetic field due to a circular loop. So if you recall rightly, you will see that the expression we derived was B equal to mu naught into I r square by 2 into x square plus r square to the power 3 by 2. So if you recall, we had assumed a circular loop and situated in a way such that the axis of the loop is along its center, and this is the radius, and the distance from the center along the axis is where we consider a point P at a distance x, and this has a current flowing through it of strength I. So then the magnetic field at this point, due to current flowing through this loop, was given by the expression mu naught I r square by 2 into x square plus r square whole to the power of 3 by 2. Now we start with this as our initial step, and when x is huge compared to r, when this distance is huge compared to this radius of the loop, then we can conveniently ignore the r square term in the denominator. So that gives us a simplified version of the expression, which is mu naught I r square by 2, r square is ignored, so you are left with x square to the power of 3 by 2. 2 and 2 cancel, so you are left with 2 to the power of x cube. Now I can also write this as mu naught I r square. If you recall, it is A by pi, because A is the area of this loop and area is given by pi r square, so I take the pi this side, so I substitute, instead of r square I put A by pi in this term, so I get A by 2 pi x cube. So I substitute this over here. So this is my modified term. Now if you further recall, in our previous discussions we said the product of current and area is something that we define as the magnetic dipole. So that is represented by the small letter m. So m is equal to the product of I and A. So I can further write this as mu naught m by 2 pi x cube. Now doing a little bit of juggling with numbers, I rewrite this as mu naught, I multiply a 2 at the denominator, I get 4 pi. To compensate for that, I put a 2 at the top, so I am left with 2m by x cube. So if you consider this particular new expression that we have got, which is mu naught by 4 pi into 2m by x cube. What comes to your mind? If you recall it correctly, you'll be amazed that you have learned something very similar in the previous chapters. Yeah, you guessed it right. It is the electric dipole, the expression we had derived for the electric field due to the electric dipole. So if you recall that particular expression, we had got that as E is equal to 2 PE by 4 pi epsilon naught x cube. So you can notice that this is very similar. If I rewrite this such that it resembles this, I can write it as, so instead of mu naught, it is 1 by epsilon naught. Mu naught can be written as 1 by epsilon naught by 4 pi as it is into 2 PE by x cube. So if you see this term is same as mu naught. 4 pi, 2m is 2 PE, where m is the magnetic dipole, PE, if you recall, is the electric dipole, and x cube is the distance from the center, along this axis from the center of the loop, in the case of the the circular current loop, and x cube in the case of electric dipole was the distance along the perpendicular bisector of the electric dipole, if you recall correctly. So these two expressions are very similar. So one is the electric field along the distance of x along the perpendicular bisector of the electric dipole, which is this expression, and this expression that we just derived is the expression for the magnetic field strength at a distance x along the axis of a circular loop with magnetic dipole M. So essentially we have seen that a circular current loop behaves as a magnetic dipole M, which is the product of current and the area of the circular loop. So the area is the planar area that we take along the plane of the circular loop. Now, one thing that you need to note, and which is also a point of distinction between electric dipole and a magnetic dipole, is a magnetic dipole, the most basic or fundamental unit is a loop, or more specifically a circular loop. This is the most fundamental unit of a magnetic dipole. Whereas for an electric dipole, if you remember, the electric dipole is actually made up of two charges, Q1 and Q2, which we had started with the assumption that these are two like charges at some distance 2a from each other. So the fundamental charges, fundamental units of an electric dipole are the charges themselves. There are two monolithic charges, whereas here the fundamental unit is the circular loop. That's nothing more fundamental than a circular loop. Whereas in electric dipole, it further breaks down into individual charges at some distance from each other. This is a fundamental differentiating feature between electric dipole and a magnetic dipole. Let us consider the magnetic dipole moment due to a revolving electron. So we already discussed the magnetic dipole resulting due to a circular loop. Now, what an electron exhibits while moving around a positively charged nucleus or a heavier nucleus in a typical atom like a hydrogen atom is very similar to the circular loop that we considered previously. So if you consider the simplest of atoms, a hydrogen atom, you have a positive nucleus consisting of a proton, a positively charged proton, with a negatively charged electron going around it in a circular orbit, something similar to the planets going around the sun. Now, this particular model was, as you know, the model suggested by Niels Bohr and is famously called the Bohr atomic model. Now, if you consider this model, you have the electron as a negatively charged particle executing, let's say over here, an anti-clockwise circular motion around a positively charged core. So this movement of the electron around the nucleus is similar to a circular loop, because as this electron is executing the anti-clockwise movement, by convention we assume that current is flowing in the direction opposite to the flow of electrons. So current is flowing in a clockwise direction in this loop. So if I consider my hydrogen atom with a positive nucleus of charge plus E, because E is the charge carried either by an electron or a proton, which is similar, it's just that it's positive in nature. And I have one electron, negatively charged electron, going in the anti-clockwise direction, which means by convention it's generating a current I in the clockwise direction. So if I were to find out what the current is nothing but charge over time. So here the charge is E divided by the time. Here is the time taken for the electron to complete one full revolution. So which is the time period of the electron given by capital T. So if I were to further expand on this, we know that time period is given by 2 pi r, which is the circumference of the orbit, assuming this to be the radius of the orbit in which the electron is executing its motion, with the velocity v. So velocity v is the speed at which the electron is moving around the nucleus. So if I substitute this back into this equation, I am left with I is equal to ev by 2 pi r. Now, I have also marked in this figure something called mu L. So mu L is the magnetic moment. If you remember, magnetic moment was something that we defined as the vector product of the current and the area. The current and the area. So we came across this particular definition when we were discussing the rectangular loop carrying current when placed in an external magnetic field. So there we found that the magnetic moment is perpendicular to the direction of the magnetic field. So over here too, if you look at it, the magnetic field is being generated due to this current, and the associated magnetic moment is perpendicular to the magnetic field and it is directed into the board. The magnetic moment is directed into the board and it's usually indicated by the letter mu L. So instead of M, we denote it for an electron as mu subscript L. Now, if I were to consider the magnetic moment mu L, it's given by I into the vector product of the area. Area is given by pi r square of the orbit. So if I substitute the value of I from this equation over here, I get EV pi r square by 2 pi r. So pi and pi cancel each other. R term cancels in the numerator and I am left with E V R by 2. So if I further multiply both the numerator and denominator terms with the mass of an electron, the reason for which will be clear in a moment, I am left with 1 by 2 me into me Vr and an extra e term. So I put E by 2me, so where me is the mass of the electron. Now me into Vr is a term which you have studied back last year. For any particle executing uniform circular motion, the product of mass, velocity and radius gives you a quantity known as angular momentum. So this me into V into R is my angular momentum, which I can replace with the letter L, where L, which is angular momentum, is equal to m, mass of the electron, into its velocity into the radius of its orbit. So my expression now becomes mu L is equal to E into L by 2 me. So this expression is also sometimes rewritten with a negative sign, typically to indicate that the angular momentum L is opposite in direction to that of the magnetic moment mu L. This is so in the case of an electron because it's negatively charged. Whereas if we replace the electron with a positively charged particle, then we need not use this negative sign in this expression because the angular momentum will be in the same direction as that of the magnetic moment. Now, taking the discussion a little further, if I take the L to the left hand side and get the expression mu L by L, which is the ratio of magnetic moment over angular momentum, which is given by E by 2me. This ratio is called as the gyromagnetic ratio, and gyromagnetic ratio for any charged particle is a constant, and for an electron it has been predicted and verified through experiments that the value stands at 8.8 into 10 to the power of 10 coulombs per kg. Now, this L, angular momentum, can also be quantized or also be expressed in the form of a quantization as per the Bohr's quantization model. So if you go back to our learnings of the Bohr atomic model, you might recall that every orbit, electrons orbit the nucleus in specific orbits. They don't have random orbits but specific orbits of fixed energies. Now, one way of characterizing the energies associated with these orbits was by using the Planck's constant. So here to the angular momentum is given in terms of nh by 2 pi, where n is the orbit number which can take values 1, 2, 3 and upwards, and h is the Planck's constant given by 6.626 into 10 power minus 34 joules second. Now, if I take the very first orbit, for example, if I consider the hydrogen atom and I take the very first orbit where there is an electron orbiting, then n value becomes 1. And if I substitute this back into this equation, I get mu L is equal to E by 2 me into h by 2 pi, where n has become 1. N has, I have assumed n has taken the value 1. Now if I substitute all these values, E the charge value, me the mass of electron, h is the Planck's constant, and the rest of them are all constant. So if I put all the values, I get a value that is 9.27 into 10 to the power of minus 24 amperes meter square. This particular value is called the Bohr Magnetron. It's an important value because it indicates the minimum magnetic moment that an electron can possess. Now, an electron, to carry these discussions yet further, an electron as it goes around the nucleus of the atom, it has two moments associated with it. One is what we just discussed. This is sometimes also referred to as the orbital magnetic moment. And it also has yet another magnetic moment which is called the spin magnetic moment. So spin magnetic moment is devoid of the sign. It's only the magnitude value of the orbital magnetic moment. So every electron exhibits or is characterized by two types of magnetic moments. One is the orbital magnetic moment and one is the spin magnetic moment. So that does not mean to say that electrons spin around their own axis, but when observed and recorded practically or arriving at the values theoretically, physicists have come to the conclusion that all electrons have these two kinds of moments. One is the orbital magnetic moment, the other is the spin magnetic moment.